Alright, so in this video I'm gonna be explaining another important article with the title Rethinking Message Passing for Algorithmic Alignment on Graphs. This paper in ICLR 2025. Most graph neural networks are based on the principle of message passing, where all neighboring nodes exchange messages with each other simultaneously. We want to challenge this paradigm by introducing the flood and EcoNet, a novel architecture that aligns neural computation with the principles of distributed algorithms. In our method, nodes sparsely activate upon receiving a message, leading to a wave-like activation pattern that traverses the graph. Yes, even in our brain, we have spiking neural networks in our brain. Not only we have sparsity in the activation, but also we have asynchronicity, and it's event-based as well. Which is very different from the conventional message passing in graph neural networks. So they propose flood and EcoNet. A key feature of FENet's execution is its sparse yet highly parallel activation pattern. At each time step, only a subset of nodes, those equidistant from the origin, are active, either sending messages outward or echoing them backward. This approach enables the computation to involve the entire graph while significantly reducing the number of messages exchanged to do so. So crucially, the FENet operates directly on the original graph topology, avoiding higher order computations. This simplicity not only preserves and leverages the graph's inherent structure, but also ensures the model's scalability to larger and more complex graphs. The FENet propagates messages in a wave-like pattern throughout the entire graph. Starting from origin orange, messages are sent towards its neighbors and then continuously flooded outwards. Once the farthest nodes are reached, flow reverses and messages are echoed back. Throughout the computation, only a small subset of nodes is active at any given time, passing messages efficiently throughout the entire graph. Moreover, the mechanism naturally generalizes to graphs of larger sizes. So the synergy between distributed computing and GNNs raises an intriguing question. Can we leverage additional insights from the distributed computing community to advance graph learning? Motivated by this potential, we propose the flood and EcoNet. Flood and EcoNet, we call it FENet in general, a novel execution framework that directly incorporates design patterns from distributed algorithms. So to illustrate the difference of our method, let us first review the conventional message passing neural network. Whenever we refer to MPNN throughout this paper, we will refer to a GNN that operates on the original graph topology and exchanges messages in the following way. So we aggregate, so this is the aggregation, and then we update it. So all nodes, in traditional approach, all nodes exchange messages simultaneously. And we challenge this paradigm by taking inspiration from a design pattern called flooding and echo, a common building block in distributed algorithms. This pattern introduces a two-phase process. First, messages are broadcast throughout the entire graph, and then information is gathered back from all nodes. This approach allows for more structured and potentially more efficient information propagation encompassing the entire graph. The flood and echo net aligns its computation flow directly with the flooding and echo design pattern. The process begins at an original node and proceeds through T phases, each comprising a flooding and echo part. During the flooding phase, message propagate outward from the origin. We iterate through distances in ascending order using two types of convolutions. fconv, which sends messages from nodes at distance d-1 to nodes at distance d. Crucially, only nodes at distance d update their state. And fcrossconv, which exchanges messages between nodes at the same distance d. In the subsequent echo phase, the message flow reverses and echoes back toward the origin. So first we calculate distances. As you see, then the encoder has a representation. Then we go through this flooding, do the flooding. And then we do the echo. Flooding is this way, the blue one, and then echo is the reverse one. And then we update it, and then we give it to decoder. So we have modes of operation: fixed, random, all. In fixed mode, the origin is given or defined by the problem instance by mark source node specific to the task. In contrast, the random mode selects the origin uniformly at random from all nodes. In the all mode, which is the third mode, we execute the FENet once for every node. In every run, we keep only the node embedding for the chosen origin. This can be seen as a form of ego graph prediction for each node. So this is the visualization of computation executed on the same graph for a regular message passing neural network. The top row shows the computation for regular message passing neural network, both for 1 and 2 layers of message passing.